Okay, I left all of this stuff here on the side here from our last example. Now, for this one, I'm looking at my 3 here, and first of all, I notice it's not just the arc sign. Arc sign would have been 4 minus x squared. This is different, right? This is one of our new ones here, and it looks mostly like what I'm seeing here. Okay, in fact, it's a little bit simpler than my last problem, because I see that my u is actually just plain old x, right? And of course, I see my a is a 2. But it is this form, so my dx, sorry, du is dx. So I have the form exactly what I need. It's already in the form, du over u squared minus a squared. So I can jump right into my formula here. I have a natural log of the x plus the square root of x squared minus 4. Okay, plus your constant. All right, so that's if you notice back in our definitions, this one looks more like the cosine. Notice x plus. So, but when we're integrating, we don't even see that. Okay. Now you could interpret our final result as some form of an inverse hyperbolic cosine, but I didn't do that. Okay, because in order to use that definition, I'd have to do some algebra in here and get that 4 out of there and turn it into a 1, basically. So I could view this as our hyperbolic cosh, but it would take a little bit of work here. I'll show you what I mean. If you take out that 4, in other words, I'm going to write it this way. Let's see, pull out the 4, right? This is x squared over 4 minus 1, like that. Okay, so factoring the 4 out, like that. And that means that 4 can come out as a 2. So we'd have an x plus 2 out here. Square root in here, but now we have this x squared over 4 minus a 1. And let's see, now I could write that as natural log, let's see, x plus 2 square root of x squared minus 1 over 2. So I can get rid of that 2. Oh, that doesn't really work, does it? Okay. Let's see. I just realized what I was doing wrong there. I'm going backwards, basically, undoing what I just did. Inside here, when I put these back together, this becomes a 4. Okay. And I'm just going to leave that. Hold on a sec. I'm going to fix that. Okay. Okay. So back from here, I have this 2. And I have a square root of x over 2 squared, like that, minus the 1. Okay, so I just wanted to view that as x over 2. Okay, and plus that c. All right, so now this is almost resembling what I wanted to, but I need to get this x, I need to get this 2 out of here, so I can factor it out, 2, but this needs to be an x over 2 then. And then this one is x over 2 squared minus a 1 plus a constant. And then using my log property, I can write this as natural log of 2 plus natural log of the x over 2 plus c. So now it's almost looking like this part right here. This is that's an inverse hyperbolic cosine of x over 2. If you go back to our definitions up here, notice the inverse hyperbolic cosine. If you replace that x with an x over 2, you'll get the same formula that we're looking at here. But what's interesting is that you still have this leftover natural log of 2, but that can be conveniently combined with this other constant, which is at this point is anything. So adding a natural log of 2 to this still leaves it as completely arbitrary. So you can just combine those two constants, and then you have that as your result. So as I said before, it's you don't want to do all that work, right? So we leave our answers in this form. Okay, good enough. It's not recognizable as one of the hyperbolic inverse functions, but it could be if we really wanted it to be. And anyway, it's good enough like that. Okay, so now let's see if we can let's do this last one here. This last one of these integrals. You can see right away that one, first of all, it's not in the form du over u, which would be way easier to do than what we're about to do. So that's not it. Always check the easy things first. But so this one most resembles our second formula here, with the a identified as a 3 and the u identified actually as an x squared, which implies du would be 2x dx. And I have an x up there, so that's perfect. I just need a 2. So I would write a 2x up there and put a half down here out in front. And if you want, you could say that's 3 squared minus x squared dx. And this way it resembles this form right here exactly. We have our du, and we have our u squared, and we have an a squared. So we know it's going to be a half times 1 over 2 times 3, because our a is a 3. I'm using this formula right here now. Natural log of the a plus the u, which is an x squared, and the a minus the u, like so, plus your constant. And then we just do a little cleanup here. This is 1 over 12. And just leave everything the way it is. Okay, so that one's done. All right, so that next time we're going to look at in the next example. Look at that differentiation.